All right, so let's look at well, let's do a couple more examples. In we're really doing 16.3. So let's do a couple more examples over here. We didn't really do an example of finding the potential for three-dimensional vector field in 3 dimensions. So let's do a couple of examples. So let's suppose that we have. Let's suppose first that we have phi x plus z squared and 2yz, right? And let's try to find. I claim that this is conservative, so let's not worry about checking the differential condition. Let's just find the potential. Right? And actually, that is one way of actually checking that it is conservative. Is just trying to find a potential. If we fail, then it's not conservative. All right. So we start with, so this is f1, this is f2, this is f3. This is supposed to be, you know, if gradient of some function var phi, some function phi is f, then we have that this is the x derivative, this would be the y derivative, this would be the z derivative, right? So we have that d phi dx is supposed to be y, right? Well, if d phi dx is supposed to be y, then phi, well, should be anti-differentiated x, so it's x y, well, plus something in terms of y and z, right? So let me call it c. Let's call it c1. We're gonna have a bunch of these, so or a couple of these anyway. So c1 y and z. It's functions of, you know, the remaining variables have anti-differentiated in x, so it's supposed to be constant in x. But of course, for each different y and z, I could get a different constant, right? So it's really a function of y and z. Right? So now, if phi has this form, then we definitely get the y, right? If I differentiate with respect to x, well, this disappears, and over here I get y. Okay, good. So what I want to do now is just let's go in order. You can go in any order that you want, but let's go here. So if it's of this form, then we get this. But when we figure out, oh, we also want to make sure that we get this guy, right? So d phi d let's see, y is d phi dy. Well, it's x plus, well, whatever the derivative of the y derivative of c1 would be, right? Whatever that guy would be, right? Now we want that to be z squared, right? So we know that because this is supposed to be x plus z squared, right? So this, whatever it is, whatever c1 is, the y derivative had better be z squared, right? So we have that this is z squared, and so anti-differentiate, right, in y, right? So c1 is y z squared plus well, some c2. Now c2 as a function of z, right? Because I anti-differentiated in y. It's not a function of x anymore, right? Because c1 was only a function of y and z, so I'm only left with with y and z. So it's right. So now let's look. We have that we've made sure that f1 is y, f2 is x plus z squared, and we need to make sure that f3 is 2yz, right? Well, for that, we know that well, let's write down what phi is now, right? What are we up to? It was x plus c1. C1 is yz squared plus c2. That's a function of z, right? Well, let's differentiate with respect to z. We're supposed to get 2yz, and we get, well, this differentiate with respect to z goes away. Hey, 2yz over here. Then we get c2 prime of z, right? So that's just a function of one variable. So that c2 prime of z should be 0. So c2 is just a constant, right? So so we really get that phi is xy plus yz squared plus a constant. If we're just looking for any potential, we might leave the constant out. It's irrelevant. Okay, so it's essentially the same as for two variables that we've done a bunch. And actually, if you are watching this, there is a two variable one on the quiz. So that was because we did the two variable one before a couple of times, right? Let's maybe do one more so that it's clear what's happening. Let's suppose that f is cosine x plus 2y 2 cosine x plus 2y and 1, right? And let's see what do we get. So we're assuming that phi, the gradient of phi is f, right? This is an arrow. So therefore, the x derivative, phi, it should be x1. It should be cosine x plus 2y, right? Well, what is that? That is, if I anti-differentiate with respect to x, that means that phi should be sine of x plus 2y plus, let's use the same notation as before. Let's call this c1 yz. All right. Now, that's well, that's what RT is. Let's figure out what's the if I take the y derivative, which on one hand is supposed to be 2 cosine x plus 2y, right? On the other hand, we know that, well, here, what do we get when we differentiate? We do get cosine, 2 cosine x plus 2y. The 2 is coming out of chain rule, right? So this looks ugly. This is an equal sign, right? Plus the derivative of c1 with respect to y, right? Well, c1 is the derivative of c1 with respect to y had better be 0, right? That means that c1 really is just a function of z. Maybe let's even write it just so that we're like here, c2, right, of z. So phi is still sine x plus 2y plus c2 of z. Now, it might seem like we haven't made much progress, but we have. We've shown that whatever is remaining is just a function of z, right? So we have made some progress from here to here, right? Okay, so let's make sure that the derivative, the z derivative is 1, right? So if we take the z derivative, well, it's supposed to be, on one hand, it's supposed to be 1. On the other hand, if I take the derivative over here, well, this derivative doesn't depend on z. So that's gone. So c2 prime, well, z is 1. That means that c2 is z plus some constant, let me call it c, right? So therefore, I have, the whole thing worked. There is a phi, right? And phi is sine of x plus 2y plus z plus c. And again, if I'm looking just for any potential function, then I don't really need to include the c in the end. But that's the way it works, right? And if you had in n dimensions, it would still be the same. Okay, let's move on from chapter 16. I just wanted to do a couple more examples of this because we haven't really done this in 3 dimensions. I've only done these examples in the plane, so and it is, you have to work a little bit to see how it works in 3 space. It's slightly more involved, but essentially the same thing. You just keep anti-differentiating, differentiating, anti-differentiating, differentiating, and you keep sort of improving on what you get from the phi. And again, just to reiterate, not every vector field has a phi, right? All right, so we can move to chapter 17. So this is sort of a big one, but this is essentially where we're gonna end the semester. But we're gonna take a few lectures to cover 17.1. So this is so-called Green's theorem, which is an incredibly important theorem in science, and in all sorts of fields. And maybe just a little bit of a backstory. George Green was he was the son of a miller in England in 19th century England, and he completely self-educated himself. He never really went to any school. I mean, he had some very minor primary education, but not even a full schooling. And but he was reading books, and he basically worked out the theory of electrodynamics, and he worked out the mathematics behind it. And Green's theorem is a big part of that. By the time he was, I think something like 30, I think, but without going to any university or school, whatever. And he published what he had. He self-published it, and he mostly, got it to his friends who had no clue what he was doing, and they just bought it to humor him. But one of these copies did get into the hands of somebody. I think at Oxford, either Oxford or Cambridge. I can't remember which one. Probably someone from Oxford or Cambridge, would get really angry at me for confusing them, because each one is clearly insanely better than the other one, depending on which one you read. And so he went there, but he soon died. He died when he was 40, so it doesn't quite have a happy ending. It has kind of a sad ending. But I guess that was normal in 19th century England. But the mill where he worked is now a science museum. You can go there. Well, not right now, but once the pandemic is over, you can you can go there, and you can see the mill where he worked and where he came up with all this. All right. So, what is this theorem, right? So maybe let's start with what we had about conservative vector fields, and said that if f is conservative. By the way, this, from now on, we're gonna be in the plane. We're not gonna be in 3 space. We're only gonna be in the plane. So in 2 variables, x, y. No z is gonna be is gonna be hurt in this. So if f is conservative, then and C is closed, so closed curve, right? Some loop like this. Then we have that. This is something that we saw, right? Now, what is this, right? I mean, this is basically, if I think of f as the flow field of some substance, right? How is something flowing, right? And it's flowing with velocity f. Then what this is saying, or what this integral is, I think 0 because it's conservative. I think I said that, but I didn't write it, right? What this integral is computing is how much is circulating around this this loop. Why? Well, because what is this? This is really the f dot the tangent vector, the unit tangent vector, ds, right? So if we were looking at the tangent vector, right, at each point, and we project f onto this, so we look at the component of f that points along this path, and then we sum that all up. That tells us how much stuff is circulating around, right? So if the stuff, whatever is going around with velocity f is going around like this, then we're going to get a positive number. If it's going around like this, we're going to get a negative number. And if it's not circulating, maybe it's all going in one direction. So, then we should get 0, right? And what we did before for conservative vector fields, we got that the circulation around any loop is 0. So for conservative vector fields, there is no circulation. That's really why for why we had the irrotational labeling, right? For locally, conservative vector fields are irrotational, right? And that's coming from this sort of idea, right? So for conservative vector fields, there is no circulation around any C. I mean, it could be that f is going along this this curve a little bit, but then it's maybe going going in the opposite direction somewhere else, and it all cancels out, right? Basically, you're really sort of summing up all these things. So somewhere it's going along, and somewhere it's going against, right? So if you had if you had a little rubber duck and it was at this point, and you computed the circulation around the really tiny disk around it. And I'm gonna draw this rubber duck, but suppose it's at this point, right? And it's floating on water, which is flowing around with velocity f. Then, if it's irrotational, if f is conservative, then the rubber duck is not going to move. And I mentioned this last time. And that's because if we look at let's put around a really tiny loop, maybe f. So you're basically looking at what the sides of the duck are doing, right? if one side is being pushed in a particular direction and the other side is being pushed in that particular direction in the same force, for example, then it's not gonna rotate. But if one side is being pushed with smaller at a smaller rate than the other side, then it's gonna rotate, right? So that's what the circulation is computing, right? And for conservative vector field or for irrotational vector field, this is going to be 0, right? Now, okay, so that's conservative vector field. Now, what does it have to do with Green's theorem? So Green's theorem, in some sense, tells us what happens for all vector fields, including conservative vector fields. For any vector field whatsoever, we want to compute this integral, right? So let's write it down in a sort of more more sort of typical notation for Green. So suppose that we have f, which has components p and q. So this is the first component, this is the second component, right? So let's call them, instead of f1 and f2, let's call them p and q. And let's look at what Green is going to tell us about p and q. Now, the first thing that we need to do is this is going to basically, we need to figure out where are we going to integrate over. So we're going to integrate around some C, which is going to be the boundary of some region D, and it's going to be so-called positively oriented. So it's going to go, so C goes counterclockwise around D, right? That's what we usually mean by positive orientation, right? It goes counterclockwise around, right? Just like basically, if you go around the circle in the standard parameterization with sine and cosine, it's precisely this positive orientation. All right. So, all right. So, what is Green's theorem? So, Green's theorem says that this integral, you write it first like this, which is the same thing as, and this is usually the sort of more standard way of writing it, p dx q dy. If you look up Green, it's probably going to be written more in this form, and that's equal to. So this equality is really the Green's theorem. It's equal to the double integral over d of the derivative of q with respect to x minus the derivative of p with respect to y, dA, or maybe dx dy, however you want to write the area form, right? So this is also dA, right? Now, another way of writing it, and this is the way that the book might write it, this is sometimes called the curl of z, the z component of the curl of f. So it might be written like this. So you might have Green's theorem could be saying as the circulation integral around the boundary is the integral over the inside of the z component of the curl. And curl is something that tells us how does something circulate locally, but also notice that if we have a conservative vector field, dq dx is equal to dp dy. So this is 0, right? So for a conservative vector field, we have that this is 0, right? So we could have used Green's theorem to prove that, right? To figure that out, right? But this works, you know, this equality, right? That's really what Green's theorem is. That works for any vector field. It doesn't have to be conservative, right? Well, if it's conservative, it's kind of trivial. This is 0, right? So here it's more. It's you have that that you can compute this path integral using this double integral. Now, this is basically a fundamental theorem of calculus. So it's used in similar ways. It could be used to compute. Could be used to compute integrals. It could be used to, you know, but now which integrals? It's you could use it to compute some double integral. If you can find a P and Q such that this curl z term, right? This dq dx and dp dy are equal to the function under the integral, then you could maybe compute it using a path integral, right? So you take a double integral and you reduce it to a single integral, right? Maybe then you could use maybe you know, you write it down in terms of some parameterization, and maybe that you can use calculus, you know, regular fundamental theorem of calculus to compute it. Now, there is a certain theme about these sort of fundamental terms of calculus, and it's if that you're basically getting some it's some integral, some n-dimensional integral, in this case 2-dimensional integral, is being reduced to an n-1 dimensional integral. So in this case, you're reducing a 2-dimensional integral over the inside of something to a 1-dimensional integral over the boundary. Right? That's always the way it will work, and it's the same thing in one variable, because you have you know, in the fundamental theorem of calculus that you've seen in Calc 1, it reduces a 1-dimensional integral to a 0-dimensional integral over the boundary. Right? The 1-dimensional, you know, maybe let me write it down. Right? It was let me write it down in this order. Right? So maybe it was I had the derivative of f prime x dx a b is equal to f b minus f a, right? That was the standard fundamental theorem of calculus. The integral of the derivative, right? You know, the 1-dimensional integral is the integral, so-called integral, a 0-dimensional integral, which is just a sum over these finitely many points, and this is an integral over the interval, and the boundaries of an interval are these 2 points, b and a, right? And this minus sign, that's really comes from this orientation, right? So here the orientation is which way it goes. For finitely many points, it's, well, some of them you're adding, some of them you're subtracting. Okay, so let's maybe see, we're not going to prove it, but let's see how it relates to the fundamental theorem of calculus in one variable. Let's look at, let's suppose that we have, let's say x is between 0 and 1, and y is between 0 and 1, right? We have the unit circle, right? Let's suppose that is our D, right? Our C is going to be this guy that goes around the D, right? So let's start on one side and we'll end up at the other side. So let's start with the integral over C of P dx plus Q dy. Alright? Now let's just write down how you would compute this integral, right? P and Q are functions of x and y, right? And so let's start maybe on this guy, right? So it's the integral from 0 to 1 of P x y 0 on this thing dx. That's the way it's going to work. You parameterize this bit of it by x. Then we do this thing, right? So the integral from 0 to 1 of q, now x is 1, and we're integrating over y. Then plus, now we're going to do this bit of it, and then it's going from 1 to 0 to get the orientation, right? Going from 1 to 0 in x, right? And we're doing p of x1 dx plus over here we're going to go from 0 to 1. That's right, q of 0y dy. Now, maybe something you're confused about. When I was, integrating over this side, why did I only look at the p term? And well, because over here y is not changing, so dy is going to be 0, right? So over this, it's just the p dx. Over this interval, it's just the q dy. Over this interval, it's just the p dx. Over this, it's just the q dy. All right. So I have this guy. Well, let's write it down. Let's write it down as some put some of these integrals together. So from 0 to 1, let's put the p's together. So I can over here I could swap the. If I swap the orientation, I would have to put a minus sign over here. So I'm going to have minus p x1 minus p x0. And you'll see why am I writing it in this sort of stupid way. So it was plus, right? Minus. And then plus the integral from 0 to 1. Let's put the q's together. So it's q1y minus q0y. And over here I'm getting this, this was for from 1 to 0. It was over here. I made a typo, right? Went from y is going from 1 to 0. Maybe you guys were confused and you can't ask questions over, if it's not live. All right. So now we have, so that's why the minus sign, right? Well, now we say, well, we're saying, so far we haven't really done anything except computing. We wrote up this integral in a funky way. That's all we did. But now we can apply the fundamental term of calculus, right? The fundamental term of calculus from calculus 1. So, for example, in this first integral, we get, well, the minus sign is there, but the thing that's in the inside, well, that's just if I think of p, for fixed x, I think of this as a function of y, p, right? So p of x, y, I think of it as a function of y, right? And then I'm evaluating it at 1 and subtracting what it is at 0. So if I apply the fundamental term of calculus, it's the same thing as integrating the derivative. Well, the derivative, I'm thinking of it as a function of y, is this, right? And now it's of xy, and over here it was dy, and this integral was dx, right? The same thing over here, I think of q as a function of x for any fixed y, right? And then this is the integral of dq dx, right? So for fixed y, I'm integrating with respect to x, right? And then dy, right? Because that's just coming from here. Well, that's putting it together. We get let me put the dq dx, and as we drop the of xy, dp dy dx dy, right? I can swap the order here, right? So it really is just applying the fundamental term of calculus twice, right? So it's not quite a proof of the term, but it sort of tells you at least why this really is just the fundamental term of calculus, just written in a funky way, right? And you could actually, if you really wanted to, make this into a proof by what you could do is you could if you look at this paper, it has I have the grid, right? So if I have a D like this, what you could do is you could approximate it by going around in this grid somehow, right? So now you have something that only goes around in the grid, and if you prove it for that grid, if you figure out what it is for that grid, well, you have it. You have the theorem, and then what you can do, instead of computing it for this grid, you can compute it for each of these little squares, right? And each of these little squares is oriented like this, right? Well, if this one is oriented like this and this one is oriented in the same way, then integral over this guy cancels, right? So you can actually, if you prove it for that little square like we did, you can make that work into why it works for on an arbitrary region D, right? By just sort of approximating everything with little squares. Okay. Where did I put? My notes fell down. Oh yes, this is what I wanted to do. So now, why is the inside thing called the curl? Why does it measure the? It sounds like it measures circulation, right? And well, so the thing is that if we let CR be a little circle of radius r around P, around some point P. Okay. Maybe that's a bad bad name for a point because we have P and Q, right? So let's call it point. What would be a good point A, right? Point A, right? That's a good name for a point, right? We're gonna let this inside be dr. It's just a little disk of radius r, right? And we're gonna look at what happens to if we have f is pq, right? We're gonna look at what happens when we let the r go to 0. Now, if we look at the circulation interval, so around this little cr of f dr or ds, however you write it. So this is the circulation interval. This is This is the integral of p dx plus q dy, right? And this, as r goes to 0, this actually always goes to 0. So we don't want to take a limit of this as r goes to 0. We want to somehow make sure that when we take a limit, it's going to go to something non-zero. So we want to somehow scale this. And the right thing to do is to divide it by the area of dr. Now, area of dr, of course, this is pi r squared, right? But you know, it's the area, right? So I could write 1 over pi r squared if I wanted to, right? And now, so this integral without the area, that tells us how stuff is circulating, but of course it's less and less stuff if it's a smaller and smaller circle. So that's why we're dividing this thing. It's basically sort of the right way of averaging, and we'll see why it's the area comes up and why it's not the length. Maybe you would think, well, maybe a length would be the right thing, right? Should be averaging over length, but it's actually the area that's the right thing. So let's take the limit as r goes to 0 of this, right? Well, that would be really hard to figure out, but if we take this, let's keep this guy, but let's replace this with what we get in Green's term. So it's the integral over dr now of dq dx minus dp dy, integrating with respect to the area. All right. Now this makes a lot of sense. This is now, seen this before, right? This expression over here, that's just the average value of this thing, right? Over dr. Now dr is a smaller and smaller disk, right? So as r goes to 0, we're getting smaller and smaller and smaller disk. We're getting closer and closer to A, right? We're taking averages over smaller and smaller regions around A. And so then the limit of these averages, well, that should just really be the value of this of this at A. All right? So therefore, this limit is just dq dx at A minus dp dy at A. All right. So we actually computed what this is using these derivatives, and it's precisely the thing that appears under the integral in the Green's term, and this is what we call the curl z, right? Curl sub z of f of this vector field at A, of course, right? So that's really why that measures the locally how stuff circulates. And that's why we had if a vector field satisfies that the curl is 0 when dq dx is equal to dp dy, we call it irrotational. It doesn't locally it doesn't locally circulate. So it doesn't. If we had this little rubber duck, it wouldn't twist around, right? So this is one way to figure out using Green's term why this is the right expression for saying that there is no local circulation. If we take the right limit, it's Green's term that allows us to go from, well, we know what this is, that measures circulation, and Green's term tells us that we're getting this integral, and well, we're just averaging it, so we're getting what's inside. All right, so we'll do more on Green's term next time. This was just some general stuff. We'll do some actual examples and some applications of it next time. This was more about what it is and how does it work and what does it tell us. Actually, I mean, in some sense, this is an application, to figure out what the curl is. Now, for example, originally, the original definition of curl in physics is really this formula over here, this limit, because that's what people want to compute. You want to compute what this is, right? That's how much stuff is twisting, right? That has a physical interpretation, right? And you could, nowadays a lot of places will define the curl as just this, but in some sense that's not what it is. That's how you compute it. What it is this this expression over here, right? That's what you want to compute. That's telling you how stuff circulates locally, right? That has physical, that is actual interpretation, right? You can say what it is. This is just, well, if I have some formula, I can compute this, right? But just being able to compute something without knowing what it is that you're computing, well, that's kind of pointless, right? So, Green's term tells you that this formula, which is easy to compute, computes this thing, which is what you want to compute, right? All right, so we'll do more on Green's next time.